Hello, everyone. In my talk, I'd like to give you an overview over our reconstruction efforts on the galactic Faraday sky using extragalactic rotation measures. In the first part of my talk, I'd like to show you how this works, what model we are using in order to connect the data to the galactic Faraday sky. And in the second part, I would like to show you which statements that we can make on the galactic magnetic field using our results. So to start off, I'd like to show you a summary of the data that we are using. So I'm relying on the 1EC catalog, which is a compilation of about 50,000 rotation measure sources. I've been able to additionally use results from the LOTS survey and the CGPS survey, although I think the latter are already in the catalog by now. The image that you're seeing is a projection of those 50,000 data points on a sky which has been divided into about 50,000 pixels, so roughly one data point per pixel. But this is not what we're interested in our construction. We want to have an image that has about 3 million pixels. So as you can see, the data is now distributed very sparsely. And one of the first main challenges of our algorithm is to correctly interpolate between those different data points. The second challenge is to correctly estimate the extragalactic component of those data points, because as you know, most likely RMs from AGMs can have a very strong extragalactic components, and this of course has to be accounted for if you want to reconstruct the galactic Faraday sky. So how do we do that? We start off by connecting the data that we have to the thing that we want to learn. So in this case, the galactic Faraday sky. And we have to account for the extragalactic noise, as our extragalactic component, as I said, and there's also observational noise, of course. And accounting for the extragalactic component in our case is done in a very implicit way, in that we simply increase the noise or allow our reconstruction algorithm to do so. Which means that we now have an unknown observational noise variance, where we just know that it's most likely bigger than what we had before. And so we have to learn an additional number basically per data point that accounts for this. The second problem, the interpolation part, is strongly connected to statistics of the galactic Faraday sky. And there we encounter another problem, namely that the Faraday sky is strongly non-homogeneous, meaning that the statistics depend on the location on the sky, in contrast to, say, the CMB, which can be modeled with a simple power spectrum, statistically speaking. So to account for this, we came up with a model that basically said, okay, we don't only have one sky map, but we have two sky maps, which we combine with the other. So we have one sky map, this amplitude sky map, which is a Gaussian random field that is exponentiated and is supposed to account for the profile of the galactic Faraday sky. So the disk, or maybe some larger features such as close by supernova remnants or something like that. And the other component is the sign field, which is again a Gaussian random field. And this, as the name says, is supposed to take care of the sign of the galactic Faraday sky, but it can also represent some structure if the structure is correlated with the sign of Faraday sky. Both of these random fields have an unknown correlation structure, and this is learned jointly as well in our inference algorithm. So basically, to summarize this, we have an algorithm that gives us not only the Faraday sky, but two component maps, which as for now only have only helper fields. They don't really say us anything. And those are the resulting maps of our reconstruction. And in order to, and this is basically the resulting Faraday sky map that we have. But I don't want to talk too much about it. I want to get more into detail what we can say about the galactic magnetic field. And for that, I have to get back to our helper maps. So this is, as I said, the model equation that we are using, but multiplying those two maps with the Faraday sky. But the motivation for this goes a bit further, namely, if you have a look at the definition of the galactic Faraday sky, you see that this is an integral from, well, the end of the galaxy, basically, to us over the thermal electron density times the line of sight component of the magnetic field, with under some Well, assumptions can be written as a product of the dispersion measure map times the line of sight average magnetic field. And the assumption is that both the electron density and the line of sight component are correlated. So, and then you have this nice formula, which looks very similar to this one, and it also behaves very similar because both the dispersion map and our profile map are positive definite, and they mostly, well, contain the disk and similar structures. While this one, of course, are also very closely related in that they mostly carry the sign, and maybe some other structure, but are mostly dominated by the sign information-wise at least. So the question is now, can we relate this component map to the galactic magnetic field? And the answer is yes, under some circumstances. What we have to do here is we have to basically fix the profile map to the dispersion measure map using additional data. This one approach of doing this has been done by us before. That is, we can use some other map as a proxy for the dispersion measure map. So in our case, we used the galactic emission measure map as we got it from the Planck satellite and had to do some things with it in order to be able to use it. But with this, you can make statements on the galactic magnetic field. Second approach that is maybe more natural for many of you is to use the dispersion measures of pulses. Pulses have this is not a new idea. This has been done, I think, for 50 years now, and pulses have the nice thing that basically they very often come with rotation measures and dispersion measures at the same time, which allows you to extract three-dimensional information on the magnetic field. And the third possibility that is relatively new is to use fast variables, because again, they come with dispersion measures and very often with rotation measures. And I will focus on the first two. And the third approach is also in the making with our methods, but this is done by someone else, by Ayush Pandey, who is also given a talk here. So to talk about the emission measures, this can be motivated by the equation which I'm showing here above. So the emission measure can be related to dispersion measure by squaring it, the latter one, and by dividing it by a filling factor that basically accounts for the statistics of the plasma along the line of sight and by the length of the line of sight. Unfortunately, we do not have information on any of those quantities of the filling factor or even on the length of the line of sight. So in our case, we then decided to not do this quantitatively, but to come up with a phenomenological model, in that we only claim that our profile map is a function of the emission measure map that we get from the Planck satellite. And we have decided to model this like this. So basically, we introduced new helper fields that rescale the logarithmic emission measure map, and then add an additional field which is supposed to account for discrepancies between different data. So it might be that there is some amplitude in the rotation measures that is not in the emission measure map, or vice versa. And we have to, and it's not possible to just get it by rescaling. You might have to have an additional component. And for this possibility, or to be able to account for this, we introduced this third delta field. And this actually turned out to be quite interesting. If you have a look at it, here you see that, so this is basically this delta field, the results of our inference in this case. As you can see, is that they are basically dominated by two blobs. And I've additionally put red circles in here, which indicate the location of our local arm. So it seems that this helper field accounts, or seems to trace the local galactic arm that the sun is sitting in. And thinking about it, this actually makes a lot of sense, because assuming that the magnetic field is to some degree aligned with the local arm, we will have an excess in rotation measures in those directions. It cannot really be represented in the emission measure map because it doesn't see the magnetic field. And there's some evidence that this is actually correct. So if you look at the Planck fast polarization map that I put below, you see a similar pattern, in that there's very little polarization in the exact direction of the local arm. And again, this is a similar effect. Polarization mostly sees the perpendicular component, and there seems to be less of it in those directions, again, seeming to trace the local arm. The second possibility that we have to make statements on the magnetic field using the galactic Faraday sky is to use pulses. Now it's a bit more difficult because our Faraday sky traces the full galaxy, and pulses do not do that. So they mostly sit within the disk, and only at very high latitudes we can somehow, or with some globular clusters maybe, we can make the statement that they're sort of sitting at the edge of the galaxy, but most of them do not. They sit within the galaxy. So we have to account for that. And we did this with our model. Well, basically we are doing this right now. So this is work that I'm doing right now. And this is still preliminary, but we are basically using additional information that we have from galactic electron density models. For example, the Yao, Manchester and Wang electron model, and also the NE 2001 model we used here, to at least have a guess for how much a pulsar is, how much line of sight a pulsar traces in the galaxy. And using this information, we can make a guess on the galactic dispersion measurement, not only the torch scales that come from the Yao model, for example, but really on also smaller scales. And having this and our rotation measurement, we can then produce a line of sight, a map of the line of sight average magnetic field. Again, this is preliminary work, and this most likely will change still. So, but still, I think this is relatively interesting. And so, this is then everything I think I want to say in this talk. Just to summarize this, we have 2 papers that are now out. This is for one, the Galactic Faraday Sky 2020 paper, which has now been accepted by ANA. The phenomenological results using the emission measure map have been published in another paper that is already 2 years old. And as I said just before, there are 2 additional papers that will come out relatively soon. That is for once the pulsar paper that I just shortly showed you. And there's also a paper on how to do a similar thing using forced radio bursts, but this is not led by me, this is led by Hutschenreuter. And the data for both the Galactic Faraday 2020 and the Galactic Faraday Sky Revisited can be, you can download at the following link. Thank you very much for your attention.